Okay, so it's recording now. I'm going to share the screen. Okay, so it's sharing. So I'm going to go ahead and start Anaconda. Okay. Okay, so we are there. So now let's navigate to the appropriate folder. Okay, and this is ITS 520. And you guys are section 1. Okay. Right, so with you guys, we've completed some of the torch tensor basics, so we did go over that. And we were working on the Celsius to Fahrenheit conversion, so we have not finished that one. So we'll finish that today. Should be, there's no way that I can catch up to the other class, I don't think, but although I would like to. All right, so let's go ahead and start the environment. So we're going to do Conda environment list. I'm going to start Conda activate I-37 ITS 520 section 1. Okay. All right, so the environment has been started. Now I'm going to just do Jupyter Notebook. All right, so this is the Jupyter Notebook that we were working through. Okay, so let's go ahead and start it up, Celsius to Fahrenheit. And let's just see where we were. I'll do a review of it, kind of to, get caught up of what we're doing, but it should be somewhat straightforward. So we got as far, as here, right? So we didn't really do all of it. So we are trying to build a model, and the model is basically trying to predict Fahrenheit given Celsius. Okay, so now we usually read data from files, and that's one of the things that we will do today. We'll just go over reading CSV files, reading images and things like that, and loading them into tensors, right? So that will be common practice. However, usually when the first model, I kind of like it to be hard-coded data, right? Just to kind of add some, simplify. So the models usually look like this, right? So I'm pretty sure there's physics equations that can be derived. I mean, there is a physics equations for Celsius to Fahrenheit. But in general, you can also have general equations, right, in machine learning. So you basically always have this general equation, a neural network, which is made up of multiple equations. And all you have to do is learn the parameters. So in this case, if we take a look, the idea is this is the model that we're trying to build. Okay, that's simple. So it takes in X inputs and it gives you Y outputs. Now this can be one single value. It could be a vector of values. Okay. And that's what that's the whole point of machine learning and what we're gonna be spending a lot of time on this semester. All right, so here the parameters are W and B. So these are the things that have to be learned during training. And then you have the inputs and the outputs. So you will need to have a correlation between this value and that value for the model to learn. Okay, so that's what the machine learning training should do. Okay, so we need to have this data basically to train our model. So we've already, so let's go ahead and let's go run these. Let me restart. So I'm going to do kernel, clear output, restart and clear output just to start fresh. Just going to leave the code in there. Now you can see all of it goes away. And now we're going to start building it up. So we have build a Celsius to Fahrenheit AI model. So I'm going to hit run. I have the equation. We've already installed matplotlib, so we don't have to worry about that. That should be in the environment. We're only using Torch and NumPy and Matplot. Okay, so that's basically it. And I hit run, hit data. Now this is the data, right? It's basically currently just a Python list. Okay, so I have T_C and T_F. So you've got the Celsius part and the Fahrenheit part. And this is how machine learning works. You usually need to have a correlation between this input value and the output value, where these could be multiple input values and these could be multiple output values, right? Or however you want to do it. So basically here we're saying that if, according to the data, if Celsius is 28, then Fahrenheit is 81.9. If Celsius is -4, then it's 28.8, and so on. Notice that this data is not exact, right? So it'll probably include a little bit of noise, right? So a lot of the data in the real world has noise, a little bit of imperfection. That's a common thing. All right, so this is our data set, just 2 Python lists. Obviously, we're going to need to make those into Torch tensors as we start to build our model, okay? Our model. So that's the next step. If you look, we take T_C and T_F, the 2 lists, and we're going to run them through Torch tensor, and now they are basically Torch tensors. We use the convention of adding the _T just to indicate that it's Torch. And then that should be it. We have our data now ready for training, and you can see, as we've seen in many examples, they are Torch tensors, okay? All right, so we printed that data basically, and you can see it there. Now the next step is basically to plot. So if you remember, Matplot has this function plt.plot. It allows you to put like the value, the coordinates x and y, right, and plot them. And this is just like either a square or a star or something. So we can click on that and visualize our data. So we can see our data, it does have a linear relationship. So you can see, basically Celsius is on this axis and Fahrenheit is on the other axis. We can kind of corroborate that because we know 32 is about 0, basically there. So that would be the point there. All right, and that's what we're trying to predict. We're trying to build a function that, given one of these Celsius that we don't have, it would predict them based on the relationships or the pattern that it finds in the data itself. Okay, so that's plotting the data. So now we're going to start with the, in machine learning, you want to think of these things as templates. Okay, when you're building a model, you almost want to think, because it can get very complicated. Okay, the architectures get very complicated, etc. So I usually like to think of things as getting the X, the Y data. All right, in this case, our X data and our Y data are these 2 variables here, right? And we're trying to build our model. Now, when we start to build a template, what that means is that there's these parts that we always have in general. They're going to change, but they can also be very similar. So I usually just say that we have 4 parts in our template, okay? And then after that, it's very object-oriented. We are not using classes right now, but we are using functions. And once we get to the regression topic, you guys will see that we can also start adding, the class, the object-oriented approach. So, as soon as, like with the other class, I'm starting this Wednesday. If you're looking at the videos, you'll see that I'll start coding things up in an object-oriented approach. So I remind you, if you haven't done so already, if you don't remember how object-oriented programming works in Python, I strongly recommend that you look at a couple of YouTube videos or something like that. It's not difficult, but remind yourself of how it is, right? It's not difficult at all. And then in general, you will learn to appreciate it. Because that's the whole point of the class. The way that I teach it is the way that I like things. So I like templates, and I like very fixed procedure or approach that maybe gets more complicated with time, but there is some logic. I don't like spaghetti code, right? Nobody likes that, just all over the place. And so this is what I'm trying to do, is I'm trying to bring structure to this stuff for you guys to see. And, for many years I've been seeing this, and it always kind of maintains this basic structure. All right, so what is this structure? Besides having functions and object-oriented programming, you can think of it as having several parts. I would call part 0 the data. That's sometimes called data wrangling, because the data can get so, it's like wrangling cattle or something. So it gets pretty wild, right? So it can be pretty tough. So it's called data wrangling, but there's a lot of things that help us with that. However, with what we're doing, this data wrangling was basically very easy, as you can see. It's like the easiest that we can do. All right. So anyway, let's think of in the template the parts that we want to have, right? So I'm just going to say that we have 4 parts. Okay, and you can give it, they don't have specific names per se, but they have a specific logic. So this is usually part 1. The order is not really important here. I mean, it's just part 1, could be part A, part B. Doesn't mean that the loss function goes before the inference function. It's just the parts that are always there, and then they work together. So there's 4 parts. Basically, I would say inference is 1. So usually this can be called a inference function or a model, okay? And usually the variable name is always model, whether it's pre-trained transformer or it's just this, it's always the model. It's the thing that takes an input, gives you an output, okay? So that's you'll see that a lot of code is written that way, okay? So that you can just kind of, the idea is if you're going to share your model, that's the thing that you would share. Or if you're going to export, that's the thing that you're going to export to your website. That reminds me also, remember, if you haven't done so already, create your GitHub account, because you're going to be using GitHub a little bit to post your models in a couple of weeks, okay, on GitHub. All right, so part 1, inference function or model. So let's do cell type, markdown, hit run. So that's 1 part, and we've kind of done this one. So it's basically you define a function model. It takes an input to be consistent with the equation up here. I'm just going to change the variable to x. Okay, so changing it to x here, but that would be the Celsius. So it's going to be the tensor that contains the Celsius data. Now, one nice thing about using tensors is that you can build a model to take 1,000 samples in a tensor or just 1 value in a tensor. It doesn't matter, right? So it's made in such a way that works. So we have x, w, comma b. These are the parameters. Now, in the future, w and b will be integrated into the model. So we're not even going to have to define them separately. But in this example, I kind of have them separately. You can always get them out of the model. They are a parameter in the model, but you will see as we start advancing, a lot of things become part of things, okay? But here, it's kind of nice to start this way. So we got x, w, and b, and then we have our formula, w times x plus b, which is the exact same formulation that we have before. That's it. This is the model that we're using for this example. And in the future, our neural network architectures will be defined here. All right, so we will be adding more layers, and so on. You guys will see that as when we start doing the regression part. All right, the next part so let me just hit run here. Okay, the next part of the template, if you want to call it that, is part 2, and that's the loss function. Loss function is also always there, okay? And as I said, loss function is probably one of the hardest parts of machine learning, understanding that whole thing. I think I've talked a little bit about the derivatives and all that. So we will come back to that later. All right, so part two, you could call it the optimization objective. So the optimization objective. And this can be also called a loss function. You know, it's just the part where you tell the model what it should do. Okay, so in this case, our goal is basically to minimize an error, basically. All right, so I'm going to hit run here. Now, the function for this kind of looks like this. So J will always denote, or in general, denote loss function. It's like the common letter used for that function. Okay, so it's basically that, J. And really, it's very simple. It is just Y minus Y, and this should be square. So I'll run this one. Okay, so this is usually the equation. And you can see all we're doing is we're trying to minimize errors. So here, what do we have? Y is usually the real value. Okay, where's the real value coming from? It's coming here. So it would be this 55.9. That's Y. And then when you take the corresponding 14, run it through the function, then this would be Y hat. All right, so maybe I should have, to be consistent with what I'm doing here, I should have called this Y hat. And you can see that there. And so this is the Y hat, the inference function itself, okay? So you can see that there then. What we do is, the logic here is that given a real value and the predicted value, we always want to minimize this. Okay, so you can think of as, in a loop, we predict with some parameters, we look at this value, and we're just trying different things until that difference becomes smaller and smaller and smaller. All right, and that's the thing that we're going to print out in our computer so that we can see that, you know, if performance is improving or not. Okay, so that's going to be called the loss function. The name of this is usually the MSE, the mean squared error. Okay, and that's one of the most famous loss functions available, and it's used extensively. We'll be doing some real kind of problems when we do the regression example, and we'll be using this function, okay, MSE, this loss function. All right, so this is MSE. I'll kind of spell it out. So it's got several names, but this is the mean squared error. All right, now let's take a look at the function itself. So as you can see, we're calling it loss fn. It's got y pred and y real, and it's the same thing as over here. So we take the difference, we square it. This is just how we do it to the power of something. In this case, 2. Take the difference of them, and we calculate a mean. So this is not reflected here because I just did this for one value. But obviously, when we're training, we might be giving it, you know, batches. Remember epochs? So we're actually just going to give it all the data. So I think we have 11 samples. So we're going to give it those 11 samples every time. So that means because they're tensors, it's just going to calculate 11 differences. Okay, so this you can think of as, this will be a tensor of 11. This will be a tensor of predicted 11. And this will be a tensor of 11 differences. You guys see that? And so obviously it makes sense to calculate the mean of that. Got it? And because it's a tensor, we can just use the built-in mean function of torch, and that's it. Any questions? Pretty easy, right? All right, so this function should be done. So now let's go ahead and run it. Okay, so we ran that one. All right, part number 3 is the training loop. That's always there. This is the main for loop. And this is a for loop. Even with GPUs and everything, it's still a for loop. And this is where you kind of give the data to your model. Okay, so I'm just going to say here, part 3. Part 3, training loop. That's, you know, good enough. Most machine learning algorithms will have this. Okay, So these three parts are essential: the training loop, the inference function, and the loss function. They're always there. So the training loop, I mean, this could just be a for loop, but it's better, I think, to create functions for everything. It just makes it nicer, more better, interchangeable. You can have multiple functions and you can just change them out. Okay, so the training loop, in our case, currently, we only have one for loop. In the future, though, we will have two for loops, usually, because when we have large data sets, we won't be able to give the model all the data at once. And so we will have to take what are called batches. We take a batch of the data, and then the next batch, and the next batch, and the next batch, and we give it all the data, and that's one epoch. Then we do a second epoch, and we start giving it all the data again, and then a third epoch, and we repeat this process, however many epochs we define, okay? In our case, we just have 11 samples, so we're just gonna give it, maybe I'll do like 100 epochs, so then 100 times we will give it the 11 samples. Now, one thing you should probably do when you're doing this is randomize the data every time. Randomize the data, make sure that when you randomize, that the X's and the Y's are still aligned, right? So you need to do it in a way that they are still aligned. Now, for this example, I'm not going to randomize it. I mean, it's going to work. So, but it's definitely necessary as we add more complexity and more data. Okay, so let's define the training loop. So basically, we've got n epochs. We need to define that parameter. In the past, I think I was playing with the learning rate, but here we're just going to give it the optimizer. So I'm going to do optimizer. That's something we need to define. Okay. Sorry, we need to define the optimizer. This is something we always have to define. This is the thing that separates NumPy from TensorFlow and PyTorch, okay? Optimizers are a thing that is necessary in deep learning. There's only one approach, really, which is called stochastic gradient descent, made up of several algorithms. All of that is abstracted, though, by these frameworks. So it's good to know the theory, but you don't actually have to implement, okay? So we'll define the optimizer. It is an object provided by Torch itself, and we will be using that. As I said, in the model, currently we are separating out the parameters, which are the W's and the B's, right? So the weights and the biases, okay? So that's kind of, we're keeping it separate for now. And then we have this, which is the data. So we have to give it, of course, TCT and TFT. Remember, we give it Torch tensors. If you try to give it a NumPy array or something, it won't work. Torch will, because the computational graph, right? I already went over that lecture. Remember, go back to the video if you don't remember. But that Torch graph needs to be made only of Torch tensors and nothing else. All right, nothing else will work. Okay, so that's our data Celsius and Fahrenheit already as Torch tensors. So now we can go over here. So I think this is where we left off the last time we met. So we've got 4 epoch in range. So this is the for loop, basically, that repeats. And basically, we go from 0 to n epochs. So we just define it. And again, this is just the number of times that you're going to show the model the whole data set. All right, so once that's done, then this is where we can start to bring together the whole logic, right? So what needs to happen is basically pretty straightforward. Every iteration, the model predicts. Every iteration, the model predicts. All right, so currently, in the first iteration, the weights and the biases are kind of random, probably, or they're all ones or something like that. So the predictions are bad, okay? But we still want to have that first prediction. That's actually pretty good because then we're going to see the performance get better over time. All right, so we have, so here you can see the model takes the X, right? And as I said, because this is a tensor, this X can be either one value, right? 1 Celsius or all 11 Celsius. All right, and produce all 11 Fahrenheit. You could also give it half. Like if you slice just half of them, then you would give it, let's say 5 Celsius, it would give you 5 predicted Fahrenheit. Okay, so that's all that's happening. The params will be basically an array that we're going to create. We use this little star here to separate it out individually. And that's because in the model, if you notice, we have 2 variables, W and B. So by giving it 1 params, but with this parameter here, we're able to split it up into the 2. Okay, so basically there we have 3 arguments in the parentheses. Make sense? All right, so that's the idea. And this gives us then y pred. Okay, now given y pred, we're going to invoke the other function. All right, and this function is the function that will compare y real to y pred. So here I have, notice, TFT, that's the real data. Okay, so denoted in our example by just y without the hat. Okay, and then y pred is what we predicted, that's the y hat. So we take the difference of them, so we give this and this and pass it to this one and take the difference. Again, if we just give it 1, it'll just do it for 1. But since it's tensors, we are giving it all 11. So it's, tensors of 11. Okay, and it takes all the differences, and then it gives you the mean basically. Okay, and that mean is saved here. So that mean is the difference, right? So if the weights and the biases are pretty good, that loss is very small. If the weights and the biases are pretty bad, that's going to be bigger, right? So our objective is to minimize that loss. Okay, so then what we might want to do is print loss, and it's usually what you do. We plot it actually. It's a generally good practice to plot this graph because it gives you visually, some indication of what's going on. Did it plateau? Did it die? Does it get stuck? And in real problems, this is where you get like frustrated because it's not learning basically, and by this. Okay, now we got one more part here, which is like the magic of Torch. All right, this is the thing. 3 lines of code are really what does everything. Okay, now there's a lot of theory that goes into this. Okay, this is why Jeffrey Hinton and his group are very famous. They came up with stochastic gradient descent. This involves calculus and all kinds of things. So we will dedicate a lecture and lab just to that at some point. Okay, and we'll do some derivatives and things like that. But for now, most of the PyTorch that we're going to do in this course will involve this. Okay, so we'll have these 3 lines of code, and they're like the magic that allows the model to learn. So if you remember, we passed something called the optimizer. Okay, that's that. So we will invoke the optimizer. Okay, and it's got one step which is called 0 grad. And the way that you can think about this is that there is a vector that holds the weights and the biases, right? And those values, every iteration have a value, right? But it accumulates. So here, what we want to do is zero it out. Every iteration, we just zero it out. So this is more of a, like a thing we're doing, okay? Then after that, we have 2 things which are called a loss dot backward. And we have optimizer step. Optimizer dot step. You can think of these as, this step is when you calculate the gradients of the function. So it's almost, I think I gave you this intuition before, right? That at the end of the day, we're updating the weights, right? We need to update them by a delta. And all we need to know is whether we add the delta or subtract the delta. Do you remember that? And that is based on, a technique, right? In calculus, that when, we have a set of functions at a specific point in time, we can calculate, do a math operation there. And the result of that is this value. Is it positive or negative? All right. So you can think of the loss backward as that step. And then you can think of optimizer dot step as just updating the weights. So the moment we've updated the values. So what does that mean? It means that when we do this W and this B now has a new value. You see that? And then the next iteration, we're going to predict with those values. And once again, calculate the loss. And then once again, do backward and step. And once again, W and B are updated and so on. So we're constantly updating W and B. Do you see that? Until they're better. Okay, because we don't randomly change the values W and B. We update them. We just basically, the formula is for the update. The formula for the update should be, I'm just going to do it for weights. So it should be weight minus, and then I'm just going to see dW, right? But this dW is multiplied times something. And this is the sign, basically. You see that? So this is the way that you update the weights. So weight equals the weight minus or plus, but minus is usually the sign used. dW is a very small value called what? What did we say it was called? The learning rate, right? The learning rate. And it's usually something you define. Usually it's going to be like 0.001, something like that. You can start there. It's a value that you have to play with considerably sometimes. But do we add or do we subtract that learning rate? You see that? And that's the power of this. This variable sign can be either positive or negative, and it tells us whether we add it or subtract it. You see, as we're doing the optimization. And that's what, so you can think of as step as doing that operation, right? The whole operation. And you can think of backward as the operation that gives you the value of sign. Do you guys see that? So we get sign first and then we update. Any questions? That's it. So this procedure is done for everything, for like really large machine learning models, for very small ones. It's these updates sometimes when you have a big neural network, right? You have to do it you get the value at the end, and then you have to calculate the weights for one layer, and that has to propagate to the next layer and the next layer and the next layer. So there's algorithms involved in that, right? So they're called the feed forward and back propagation algorithms. But anyway, all that magic and all that very complicated stuff is done with just those 3 lines of code. Okay, and you will see most of our machine learning examples that we will do for a while this semester will just involve these 3. Okay, the order of these, this can be at the end or at the beginning, doesn't really matter, but the order, yeah, is usually backward and then step. All right, and that's it. That's the loss function. Okay, that's part 3. Then now what we have to do is, obviously we're almost done with this example. The next step is we're going to call the function training loop, but we also need to define some of these things, right? So let's see. So I think we also need to bring in, so let me go up here. If you notice, we created a variable called optimizer. That optimizer is provided by Torch, so we need to import it from Torch. So we just say import Torch dot optim, which just stands for optimization, right? So these are all the modules for optimizing our model. And so from torch.optim is where we're going to import whatever we need. So in this case, we're just going to call it as optim, something. All right, and now we can grab stochastic gradient descent from it. There's basically 2. In general, I have used just 2 optimizers. Stochastic gradient descent, and then there's another one called Atom, and Atom is like a more optimized one, so it can be a little bit faster. It's got some error corrections, etc. All right, so hit run on this one. Make sure it works. Okay, so it seems like it worked for me. Okay, so now in here we're going to go ahead and define the parameters. So params was the first thing, right? Params equals, so that's this variable here, which is this variable here, which goes in the model, which it basically is W and B. So it's it's 2 variables or a vector of 2 that we're going to split up. So here we can just create, you know, we've already done a lot of examples of this, how to create torch tensors. So in this case, we need a torch tensor. We're going to define it to be what? There's two values. Now, in the future, we will initialize these in a much smarter way. Like we're going to initialize these to be random and with normal distributions, things like that. But for now, it could be pretty much anything. So 1 point. This model is easy, so it should learn. So we're just basically saying initially the W is 1 and the bias is 0. That's it. Okay. But that's the thing that's going to change. And then we need to say, this is a thing of torch. You need to say, because remember, when we do this, right? I've already explained this in a video, but we do this and then we link it to the loss. Remember that model is YPRED and this get linked, right? All of it. We talked about the computational graph. So we need to tell Torch which parts of the computational graph are things that it needs to calculate derivatives for, the so-called gradient, right? That procedure. And so, you know, we just explicitly can say for params, which is the W and the B, which are the things in the computational graph, we want it to whenever we run backward, we want it to calculate the gradients. And so we literally say requires underscore grad equal true. Why is this handy? Because sometimes, as you will see later on, when we're doing, we might be running we might be predicting on the training data, and then like we also want to see a performance on another data set called a validation data set. But we also don't want the model to learn from that validation data set, right? We only want it to learn from the training data set. So this comes very much in handy because we can say, okay, requires grad equal true. And then we're going to do the evaluation and we say requires grad equal false. And then it's not going to learn from that. And then once again, requires grad equal true and so on. Do you see that? It's like a switch that we turn on and off to update the weights just by doing it. So it works really nicely. Okay, so that's done. Then we've got the learning rate, right? Which we always provide, learning rate. So that's going to be a value. So this is, you know, in our case, I usually try things like 0.001. I try 0.3 zeros and a 1, and so on. You guys see that? So this is kind of what I like to do. This 0.001, it's a challenge, okay? Or figuring out the learning rate. Now, there are techniques for finding the learning rate, but it can be a challenge. So once we start with regression, depending on how hard the problems are, you know, we'll just have to figure out what the right learning rate should be. Got it? Everyone get it? Yeah. All right, good. And then, so that's the learning rate. And then the last part is the variable optimizer. So that's this one over here, right? So we need to define that one because we're going to pass it to the function. So I'm going to say optimizer equal optim, y optim, because that is this optim over here, right? So I'm going to do optim there, and then I'm going to choose whichever one I want. So in the future, you might see me write that. That's the atom optimizer. But because this is the first example, SGD, which is stochastic gradient descent. And that, like I said, is the algorithm that made Geoffrey Hinton famous. He says that there were several groups that came up with this, but his paper came out in 1986. So you can see, you know, it's been around, what is that, like almost 40 years, right? 35 years or so. And yeah, that's how old, you know, that's when they figured it out. And astonishingly, everything gets trained on this procedure and nothing else. There is no other one. And so we are kind of like stuck with it in a way, you know, so. But it, you know, they haven't, because Atom is not another one. Atom is just like improved little tweaks here and there of the same idea. And it's actually, remember, it's several algorithms. So at some point, I will give you all the papers for you guys to read. And like I said, we'll break this down a little bit into some of the details. But there is no need for you to ever code this. Like, no need. You'll never have to do that. So even before Torch and TensorFlow, you still had solvers that would do this part for you. All right, so let's go ahead and wrap it up here. So then stochastic gradient descent, we need to tell it a couple of things, because this is the you know, the how we're going to learn, where we do the derivatives. So we need to tell it that params is the thing, right, that we're optimizing, the weights and the biases. So that's the tensor. Now, this was a question I had in the other class. Why the square brackets? And apparently the way, remember, the way the function is defined sometimes, it's very specific. And so the way that Torch was defined for is that basically it wants a list here. Okay, so that's why we put the square brackets, even though this is a Torch tensor, as we see, well, right here, right? So it's a Torch tensor, but it wants a list. So it might be because you provide several things. That's what I'm guessing, right? That you can give this thing several things in order, and you know, it wants a list there. You can read the documentation and see exactly why, but you know, sometimes it's like that. You just kind of have to follow what they want. All right. And then the other thing that you usually specify here is the learning rate. So it's got this argument LR. Okay. And so here we just provide learning rate. We could have hard coded it, but I think it's always better to have parameters defined as variables. I usually like to define these at the very top of the code when we start to get into code that's really long. All right, so continue to break it into a template, right? And so some of the machine learning models, as they get more complicated, they'll have 20, 30 parameters, right, that we have to define. So get used to that. All right, but for now, this is fine enough. This is fine. All right, and that's it. So these are the 3 parameters that we define. So hit run. And now all we have to do is invoke the training loop. So the training loop is what? Is this function, right? So we're going to call that function and give it all these parameters, basically, and run it. We know it's going to print the loss. We know it's going to have the models. The models up here is almost like a global variable. So we can basically use it later at the end. We're almost done with this one. So does the function does not return anything. Which part, sorry? The first one? Oh, did I forget to do that? Okay, yeah. That one? Yeah. So I ran it, thanks. All right, so now let's just invoke the function. I mean, here it's not returning anything. You don't need to return anything, so it could just be training loop. Oops. Training loop, right? Now we do have to specify the parameters. This is just for those of you that have done web development and know jQuery and all that stuff. That's kind of a jQuery style of coding. It's just because they got so many parameters. So what are the things we need here? N epochs. All right, so how many epochs will we need? Probably not that many. Let's just do 30. See what happens, how good it is. What else do we need? So we have to follow the order. So optimizer is optimizer. So optimizer equals optimizer, right? This is the one we define here. So that's what we're passing. Then the function needs params, which is that variable there. So we can just say, oops, params. Equal params, right? And the last 2 things that it takes are the data itself. So the Celsius and the Fahrenheit, the 2, remember the tensors. Notice I wrote the _t there to be explicit. So let's say t _ct, comma, equal to basically t CT, comma, and then finally TF, Fahrenheit T, TF T. There we go. And that's it. That's our function. So now, I mean, it should run. All right, so, and then once we're going to train it basically and see what the performance is like. And then there's a couple of ways to measure performance. Obviously, we're going to need to do that at some point, performance metrics. But for this time around, we're just going to keep it simple. So it should work. So hit run. Okay, or not. RFT. All right, so I have a typo there. Okay. Try it again. And epic. Okay, probably epics. Yeah, and epics. And there we go. So that's what you should get, right, guys? So that means it's training. The law, it's every iteration, it's printing the law. So the first law, 1763, is really high. Why is that? Because the W and the B were 1 and 0. So they were not actual. In fact, what we were doing is we are making that B 0. So it was really just 1 times that. It was really, X was equal to Y, right? So not really very good. But over time, those parameters get updated. Do you see that? Would you agree that the loss has gone down? It's gone from 1763 to 432. Do you guys see that? So constantly it improved, right? See here it's in the 960, then 650, 500s, then it kind of goes to 400s, and so on all the way down. Any questions? All right, so now what do? So this means that we've trained the model for 30 epochs, right? And we've got W and B's, weights and biases, that are now, parameters for the model. So what do we do next? We want to do a prediction, right? So then I'm going to do Y. I'm going to predict. What do I invoke to make a prediction? The model itself, right? This function, right? This function. And I need the W and the B's from optimizer that it's trained. So then I'm going to just call model, the equation itself, parentheses. I'm going to give it an X value that I want to use. So I need to define that X, right? I need to define X. And so we'll think about that. Any questions, guys? Questions? All right. So we're going to give it X, and then we need to specify the params here. So we're going to use the asterisk params to break the parameter into W and B. All right. So remember, this is params, this tensor here that is linked here to optimizer. So optimizer updated it. All right. So now that I have this, I can should be able to do a prediction. So one temperature that we know in Celsius is 0, right? What's the equivalent of that in Fahrenheit? 32, right? Is it 32? Yeah. All right, so 0. Let's start with that because that's one we all know, right? So 0, run, okay. And then now we're going to hit Y, right? We just want to see the value. Does that make sense? All right, so when we run Y, the value is 0.94. What do you think of our Celsius to Fahrenheit conversion model? Not good, right? Not good. Yeah, it's not good. Oh, no. So what do? Train more, right? I did 30 epochs. Maybe I need more epochs. I could also change the learning rate. Obviously, more data would be good, right? So we only have 11 samples. So do you think 11 samples will be enough to train the model? Maybe not, maybe yes. I don't know, right? So that's what machine learning, that's the beauty of machine learning. So that machine learning, you get your answers, right? You don't have to wait for anyone to tell you what they are. You can just play with it. So I intentionally made it 30. What do I increase this to? 1,000? Sure. Or 3,000. Why not 3,000, right? You can do a lot. All right, so let's go ahead and do that. So now I'm gonna hit run, and you can see it's still thinking, processing, I think. Okay, it finished. So we were in the 400s. Notice it's now in the 300s. That's good. 200s, that's good. 100s, that's really good. 90s, perfect. 80s. So it keeps going down, right? So it went all the way down to 12. That's actually a big difference from 400. All right, so we've trained the model now. So before it was 0, right? So let's see now. We have the equation with the right parameters. What do you think? It predicted 30 now. A little bit better, right? A little bit better, more. So yeah, so that's what that's machine learning, right? So if you were in the 1500s, I don't know, did they have that equation already in the 1500s? If not, you could have used Torch back then to win a Nobel Prize. All right. All right, so yeah, that's it. So in the other class, they had a very interesting Celsius that I didn't know about. They told me that there's one situation where Celsius and Fahrenheit are the same value. Do you guys know which one it is? There is a situation where they're the same.
-40. They meet.
-40 apparently. So this won't be exact, but if you look it up, apparently it is. So -40 Celsius should be around -40 Fahrenheit. Yeah, so the model here gives us -47 because it's not perfect. But if you look it up online, you'll probably find that they're very close to each other. Question? Yeah. Yeah. Sure. Training loop? Uh-huh. Or the definition of training loop. Okay.
So if you increase the learning rate, that will, within 3,000 epochs, you probably be able to converge even
Better? Did you try it?
I don't know.
I mean, you can't. These are the things you should do, right? So
you
we
want
can
to-
do it.
Yeah.
We can totally do it. I mean, that's the whole nature of machine learning, right? So machine learning, there's no science to figuring this thing out. You got to play with these
I
parameters.
was actually thinking the reduce 1, 0.
Oh, reduce.
What do you
Okay.
think? Because,
I don't know.
because it's I think because after 3,000, it's
Try it.
way too slow.
I don't know. I mean,
But it should come down to 0 faster.
so let
Because
me,
right now it's after 3,000, it's still at 12. I mean,
Nan.
oh,
That was a good, I'm glad you brought it up, Nan. Do you see this, guys? Infinite. It was getting very small.
Yeah.
Right? The value is getting, so it went here, then it got pretty small because it's exponential, and then it got infinity, basically, it's saying, and then you got Nan, not a number. So that actually brings up a very good point. Why did this happen? Because I'm using a loss function that I define the equations for. And this is common when you define your own equations. This is why you will see later on that instead of using the equations like this, we're just going to use the built-in torch MSE. So in the future, this will just be torch.msc. Why? Because that function will never give you a nan or an infinite. It just handles it. You know what I mean? It's got the, this was an underflow thing. It got too small and it couldn't just do the operation. But when you use the functions, it's got error handling basically, so that this doesn't happen. Yeah, so yeah, that's it. So there's a thing called clip. So you would have to add here like something called clipping, and then you won't get the error. But it's better just to use the built-in system.
so right now it won't. Once you hit NAND, it won't work anymore.
It broke, yeah.
Oh, it broke.
It literally
So
broke.
if then see if we can count, because we got really good when it,
We'll just do fewer epochs. I see where
Yeah,
you're going with
yeah,
this.
so we just do like,
I think it's like 20 epochs maybe.
yeah, it's already good enough.
So you
Once
just-
you hit 1 point.
Huh?
And then they just keep growing, now you can keep growing.
The air, is it growing? Oh, yeah, you're right. It's actually getting bigger. Yeah. Good observation. It's actually getting bigger. Yeah.
So I see.
Yeah. So he's right. So I didn't notice that. So he's right. It's getting bigger. So that's why it gave an error, right? So
Oh, I see.
welcome to machine learning and dealing with parameters. Literally, this will happen to you a lot, but thankfully we will have functions like, as I said, MSC, just use the built-in, or yeah, it's the best approach. So actually what I would recommend is do the, I think 3 zeros, right?
Yeah.
We had 2 initially.
2, yeah.
Yeah, we can try that as well.
And then increase the, ethics again.
Yeah, so let's see what happens. I'm not sure what will happen.
Go down to.
It's at 300 right now. 200. So we may need to add more epochs.
Yeah.
Is it go? We'll actually see it plateaued at 281.
Oh.
You see, it's kind of like getting very stuck
Hmm.
at 281. But let's add the 6. It finished, right? So it got, well, I don't know where it's gonna go. I can't predict. I mean, all I can do is experimentally try. Let's just give it 4,000. And let's see if it gets below 281. It's thinking.
It is already below 381 right
Yeah.
away. 275.
But that's only because it's using the model, I think.
Yeah.
I haven't flushed the model.
One thing is, we want to go back to 2 zeros, because right now you had 0001 learning rate. Is that,
Yeah.
it was not, originally it was 3,000 epochs, but 001.
It's probably, I think it's 2 zeros and a 1, and then more epochs is probably the way to go.
Yeah,
I would say.
yeah, so if you go back and change it to 001 with 4,000 epochs. No, 4,000, because we've already done this with 3,000. If we go to 4,000 epochs, that will probably go below.
Any questions, guys?
This is what we got before.
Yeah.
Yeah, 95.
95.
If you go to 4,000, then it probably go below 95.
Possible.
Yeah,
It's in the zone. I think I'm not flushing the, like it's keeping what it trained on
Oh,
before.
I see. So
Yeah.
we started with 95.
Yeah,
Yeah.
it's kind of like that, yeah. Yes, sir.
Output like that, so it doesn't just go on screen.
It's just doing it on my Jupiter. And my Jupiters all usually just do this. $54, getting kind of stuck.
On that one side.
Uh-huh. On where?
You click on the left side of the enter,
The one, oh,
scroll down a little bit, go down a little bit, to the right, go up, inside the box, over, right about there. If you click inside there,
on left of the word, so.
Oh, okay. Nice. All right, I didn't know that one. Okay, yeah, so what do we want to do? Can we create a plot of this? We're done, right? Do you guys agree that we're done? Now, I think let's just run it from beginning to end so that we get back to, so restart and run all will pretty much clear everything and run the whole thing, right? So it's thinking. And it's gonna give us, all right, so it printed out the losses. 11, which is as far as it's getting there, 10. Like I said, from here on out, I mean, I usually just leave it to you guys to fight with it. So there's no science to this. It's very experimental. This is where you start reading papers and you start to like, okay, how do I get because you want to squeeze more out of it, right? More and more and more. Okay, anyway, all of our problems will be like this, and they'll gradually get harder. All right, so we did the training and prediction. So it predicted minus 42 for minus 40. That's pretty close, right? Before we were at minus 40 and minus 47, this is minus 40 and minus 42. Even better, right? And this is why, if you think about it, I cleared everything and did it again, which also shows you a little bit of the nature of this, that you may run it one time, and then the next time is a little bit different. You see that? And maybe a little bit better. So this happens in machine learning. And this is like in Torch, it's doing things, right?
Probably because the stochastic, because it's random.
It's random. It has some randomness in there. And so it's basically one time it does it like this, and the next time it's like, no, I'm going to do it this time. You know what I mean? So those are built-in things. So you will never get the exact same thing. And that's why it's good to run like multiple experiments and think of out of like the average of them. It's always good. And this is why we do multiple epochs and so on. Got it? All right. The thing that I was thinking about is in the time that we have left to wrap, and this will wrap up this problem, is to create a plot for this one, right? Now we've already created a plot for the data. So it actually could be easy, right? We know that if we create a NumPy array, right, of values that are aligned like these, then we can just use plot. Do you guys see that? So I would probably want to create, yeah, let's do a plot. Plot should be okay. So what do we need to do to create a plot of the losses so that we can see the actual shape of it? What do you guys think? What do we need to save? The loss, right? The loss would be on the y-axis, and what would go on the x-axis? The epoch, exactly, the index. Very good. So then all we need to do is here in the for loop, let's see, you guys can help me out, but I think if we just create a list of epoch, because our for loop goes from 0 to n epochs, and every time we're calculating a loss. So we've got a loss and the epoch, we're going to end up with 3,000 points, right? So that's actually works out easily. So list of epochs, right? And it's just a list in Python. And then we have list of losses, right? And that should be that easy. List of losses is also a list. So now we're just going to create the data that we need so that we can plot it. Now this actually, because we need it at the end, right? We need it at the end. So I guess I can return it. Yeah, I'll return it. So then I'll return. I mean, we'll probably just do global variables, and that's even easier. All right, so let's just do it like that. So then here, all I need to do is save them, right? And I don't, and then I'm just going to use them to plot the losses basically. So in Python, obviously to add values to a list, you just do append. And over here, we just do dot append. Right? So then what do we append to epochs? We just append epoch, right? That's the variable that should control the index. And then to this, we just append loss. So that's it. We should be able to plot this now. Let me copy this code over here. Okay. So now what I'm going to do is, where would we want, after the training, somewhere around here in the end, maybe, we would want to plot, but we need to plot those two lists, right? So list of epochs and list of losses. How do you convert Python lists into NumPy arrays? Because we know that this function likes NumPy arrays, although this function may take Python lists. Let's try that. Matplot is very, very powerful. So it may actually just. List of epochs should go on the x-axis. List of losses. Should go here. Right? Right? Everyone with me? So. Nope. It's not list of epochs. It's not. Did I not run it? Oh, I need to run it probably, right? Okay, so let's try it again. Ran that. Run training. Okay, it finished. Try the minus 40. Gives you minus 42. Now let's try the plotting. Yeah, can't call numpy on tensor that requires grad. Okay. Loss. Okay, so this is an interesting error that you were gonna get a lot. Tensor.detach.numpy. This is a very common thing, error in PyTorch. What does it mean? It means that matplotlib encountered a torch tensor. Do you guys see that? Why? Because it tries to, it doesn't care about the epochs, right? So the epochs is not the problem. The problem is list of losses. What is list of losses? List of losses is made up of all these individual loss values, and all these individual loss values are the result of doing torch operations. Do you guys see that? So loss fn, right, gives loss. But this is the computational graph. Got it? So that loss is in the torch graph. And therefore, it's telling you that it cannot do this operation on something that is a torch tensor, especially because it requires grad, right? So it's part of that. So, but it gives you the solution right there. It just says, can't call numpy on tensor that requires grad. Use tensor detach.numpy. Do you guys see that? That's basically what we would have to do. So my suggestion is that here, we do that. You see that? Where this tensor should be what? Loss, because loss is a tensor. So what you're saying is you're going to take loss, detach it from the graph, and then once it's detached, make it into a number. Got it? Does this make sense, guys? Another torch thing. All right. So let's run it again. You've got to double check that that it's not affecting the computational graph as it's learning. Otherwise, we would need to do it after the training, kind of like detach it there. So that may be a thing. So I'm just testing this to see if it'll work. So the way to test it is just to make sure that it does learn, right? So I'm actually, you know what? I'm going to go, just to make 100% sure, I'm going to clear the output. These are the things where you kind of have to go back and play with it. I stress this error because we're going to see it a lot. It happens a lot when you're trying to see performance at the end. So, okay, so now I have fresh everything. Okay. Let's go ahead. Okay, so this is the training function. All right, so it's training now. It is learning, so okay, good. This was my concern, detaching the loss and affecting the learning. It seems like it learned, right? So then we do the prediction here. And that's minus 42, so that's good. So now hopefully it'll work. Ah, okay. What do you guys notice? It's not the nicest graph. So we could make it nicer for sure. But what do you guys think? What do you see? Does it make sense? It learns, right? So it's going down and it just like learns. It's 4,000 iterations apparently. Yeah, that's it. So this is how you, I mean, there's better ways. I think this plot functions is actually not the best. I want to say maybe scatter. There are other ones. And I just don't remember the exact name right now. No, that one doesn't work. Plot maybe. Let's stay with plot for now. So you can see that at the beginning, right? The interpretation is there's a few points here. And then, yeah. But as we move forward in the semester, we'll look at better ways of plotting the data. So it's a little bit more descriptive. All right, any questions? That's it. All right, so it's 6:17. All right, this concludes the Celsius to Fahrenheit model. This was your first torch model, okay? During the second half, we're just gonna go over, so let me stop the video actually.